Welcome to this Quantum Security and Defense presentation, Quantum Certification on-Chain, and thank you for being a valued member of our community.
Paulo A. Viana is a mathematician and computer scientist working at the intersection of quantum computing, post-quantum cryptography, and algorithmic design. He holds a BSc in mathematics and an MSc in computer science from UFPE, where he developed a Grover-based quantum genetic algorithm to solve the max cut problem. Paulo is currently chief scientist at Quant.Bond, leading research on quantum algorithm verification and post-quantum infrastructure. His prior experience includes a position as quantum computing analyst at Accenture, where he co-authored a patent for a novel dual-unit quantum genetic algorithm for nonlinear optimization. Paulo is also an active contributor to the Quantum Computing Academic League at UFPE, where he lectures on post-quantum cryptography and coordinates research in quantum-safe protocols.
Well, thank you, Anna. Thank you, Oscar, for the presentation. So I think I'm going to go to the same vein of presentation that Oscar did, but this time is not a fictitious startup, it's a real one. So we are Quant.Bond here. Let's start the presentation. So the whole deal with dealing with certification is a problem in the industry. So we have quantum software land in one side, on the left here, and industry land on the right side. And the real problem here is to connect both so we can get adoption for quantum software in the industry. So this is the deal we're dealing right now. And the first thing we think of is quantum hardware. So we need more qubits, we need to advance in the hardware part, and that's obvious. That's the first answer. But there are other issues that people don't usually think about that are a consequence of it. So the first thing you can notice here is that in the industry, they have requirements to work. And the first one will be reliable software. You cannot just deploy software, not any software. We have reliability. We usually, for critical infrastructure, and post-quantum cryptography is an example of it, we need some reliable software. So that's why for cryptography side, standardization is really important. But for other optimization problems, for example, other issues, it's really important that we have reliable software to work on. Second one will be standard library that industry requires. So it doesn't matter if you have an algorithm, you should have an optimized version of it that can run and deploy quickly. So that's why usually businesses are looking for. And the third one will be intellectual property. So if you have an algorithm, you should defend your algorithm property usually. And for quantum software, this is not really simple to do. So for classical software, there are some problems with that, but with quantum software, the problem is deeper. So we're going to look further into that. So our solution is to bridge those two. So we're going to basically solve this problem and fill this gap. There's $1 billion market cap right now. So we have an MVP and for this solution. And first thing we need to do is funding for quantum software research. So there's a problem in funding for quantum research right now. And the industry is growing, so that's good, but it's not enough for getting high quality industry use case software. So we have MVP, it's called NOT, the MVP, is a post-quantum cryptography algorithm. And to do the funding, we launched a research project token. And with this support, we were able to develop more and to start some research and do some real good science here. So we got a trade volume here for $55 million, and we got a market cap for the project about $15 million. So we were able to do this to get this research side of things and to cover it. But this is the first step for our solution. And the problem is not only have funding, but we also have a problem of reliability and IP protection. And this is when we notice, okay, the problem is deeper for quantum adoption. It's not only about funding the research for scientists, but it's also about how the industry see quantum software in general. So here on the left side, you can see the problems that the industry have with quantum software. And the right side is the consequences of it. So here you can see Oracle construction. So basically, you have a quantum algorithm, you have a deep layer. So we have a more complex type of algorithm. And it's not simple to check and verify if the algorithm is right, if it's running optimally. And this is an issue. People try to do that right nowadays, but it's simple because we have simple algorithms. But as time goes on and the industry got more mature over time, this will be a very deep problem to deal with. So quantum algorithms, they are non-deterministic. So it means that you cannot run many times the same algorithm and you can get different outputs from it. So as we know, it's not simple to do this and check if the algorithm, there was some plagiarism to it, or if it's optimized to it, or if there are bugs to it. So it's hard to verify its correctness. But as a consequence, so we can get quantum bugs. So you have an algorithm that's working for some optimization on the oil grid or some critical infrastructure, and we have a bug on this quantum algorithm. So the efficiency is much lower than expected. You don't know why, and you cannot simply debug or verify. So it's costly to do it, and sometimes nowadays we have some fake breakthroughs that happen. About 2 years ago, there was some paper that come from a Chinese institution that claimed that they broke RSA with current quantum hardware. Took some time, but people checked, and okay, that's not really what's happening, even though that was the claim. But it took time, effort, and money to check. So there should be a way to do it easily, cheaply, and that in long term will be easy to do.
Watch the full presentation, plus many other expert presentations. Enjoy training, community membership, and more. Simply search for Quantum Security Defense.